All right. So, on our things to do today, don't forget you have your last mastering for Chapter 8 tonight, and our exam is on Wednesday. And since I got no questions over the weekend, I'm assuming everybody did the practice test and aced it, and there's nothing you guys want to cover for the exam? Oh, just kidding. Okay. Yeah, Sarah. Tell me what your number one reads.
What?
Tell me what your number one says, because I have old versions of it.
It's how many grams of trilithium nitrate can be formed from 1.75 moles of lithium?
Okay. All right, let's see. So the question is, I see why that's tricky. We haven't done that yet. Ignore that question. Let's do this one instead. So like number one on your practice test, how many grams can be formed from this? Blah, blah, blah. We haven't done that yet, so you can't do that problem. You could do that problem, but let's do this one instead. Oh, yeah. So the first question on the practice test is from Chapter 3, and we didn't cover Chapter 3, so ignore that first question. Ask this one instead. So let's say I have that many moles, I'm going to go from moles to grams. That's the question I actually want to ask. So what unit are you given? Moles, right? So you're going to start with that. And what unit do you want to go to? Grams. So what thing do you need in order to be able to go from moles to grams? What's our conversion factor for things like this? Molar mass, right, or atomic weight. How would I go about figuring out the atomic weight of something that has 3 lithiums and 1 nitrogen? Yeah, the periodic table, I would need that. So looking at lithium, we're going to round. Lithium weighs about 7, right? And how many lithiums do I have? 3. And then nitrogen weighs, we'll call it 14. So what would that mass be all together? Let's see. 21 plus 14. What would be my units of atomic mass then? Where are they always? Grams per mole. All right, so now I have 1.75 moles of this, and I have its molar mass. So do I use its molar mass as is, or do I need to flip it upside down? As is. Let's see what that turns out to be. And then what would my units be?
Grams.
So that's the one from Chapter 3 that we...
No, this is the one from Chapter 3 asks you to use a balanced chemical reaction to predict hemi products.
Okay.
We're not ready for that yet. I could totally ask this though, because it's just unit conversions.
Would you do this using that calculator, or is this
If I want to use Avogadro's number, I have to ask a different question. I would have to say, so if you see the word atoms or molecules, that's a key word that says use. Right, so if you see the word atoms or molecules, those two words mean somewhere in your math you need to use Avogadro's number. So I'm looking for the smallest amount. Yes, sir.
Could you do number 15 as well?
15. Can you read me your number 15?
Calculate the energy of a photon in electromagnetic radiation for 601.5 nanometers.
Yep. 628.5. Okay. I shortened the question, but that's right. Calculate the energy of a photon. If you know the photon's at 628.5 nanometers. So what am I looking for? What's the final thing I'm looking for in this? Energy, right? I'm looking for energy. And there's two different equations we have that talk about energy. Do I want to use the one that involves lambda or the one that involves frequency? I want to use the one that involves lambda because this is lambda. All right, so we want to use that one. What is H? It's a constant. Blank's constant. And I will provide all the constants. You have to know the equations. There's only like 2, 3, so not that worried. I'll give you all the constants. That way, in a moment of panic, you don't get the wrong exponent. All right, and then what's C stand for? All right, the speed of light. Put that in. All right, what do I still need to do in order to be able to finish solving this problem? Convert to meters, right? Because otherwise I have a unit error. How, I guess, do I put meters on the top or on the bottom of this little fraction? Put on the top. And then, is it positive ninth or negative ninth nanometers per meter? Right, if we're at like that, it has to be a positive number because there's a bunch of nanometers in a meter. So you can think about this, right? A nanometer is the width of your hair, so you're going to need 1 with 9 zeros to equal a meter. All right, so then we're ready to do a little this, a little that, this, that, this. How many significant figures do I get in my final answer? 4, right? 4, because I had 4. Well, I guess 3. Yeah, you're right. The zeros. So 3. So 4, 3, and 4. That's conversion factor. That's count. So I get 3 in my final answer. So 3.16 times 10 to the negative 19th. And then what would be my final units? Joules.
That's the thing that I don't get, because I kept doing that problem, and for some reason I kept getting 10 to the 31. I'm not sure where I would have gone wrong.
10 to the
Because I got the same answer, just different magnitude.
I'm guessing it's plugging in this 34 has to be a negative. Doesn't, or you didn't have your the 9 and nanometers has to be positive. It's on the bottom. You had If you had your exponent with the wrong sign, it would throw off that.
All right.
Yeah. Other questions? Yes?
Number 3, can you explain what an atomic element is and what the correct answer to that question is?
Sure. So an atomic element is an element that's found always by itself. It's in chapter 2 in the reading. We covered it a little bit. But an atomic element is an element that's found in nature as a single atom. So of the things that are listed, as a rule, all the halogens are found in pairs. Bless you. So it'll always be Cl2, I2, Br2, what element am I missing? F, F2. Those guys are always found in pairs. H, O, and N are also always going to be found in pairs. So it's always going to be H2, O2, and N2. And those are the elements that will always, always, always be found in a pair. So the only ones on that list that's not on my list was magnesium. So magnesium is totally fine just hanging out by itself, being a solo element.
So bromine is always found with B?
Yep, everybody that's a halogen, chlorine, iodine, bromine, fluorine, always are in pairs. And the only other 3 that we care about are going to be hydrogen, oxygen, nitrogen. Yeah.
I have a question concerning the radii.
Mm-hmm.
Whenever ions come into play, because it's not the same trend. So are there like rules that?
Yeah. So in terms of, let's see, I have my picture of ionic radii. All right, so this is our ionic radius. And so there's 2 trends. One, if it becomes a positive element, so group 1, 2, and 3, right, go from a neutral element to a cation, those are much smaller. So if it becomes a cation, it's a smaller radius. But then it follows kind of the same trend that as you go from lithium to beryllium to boron, so you go left to right, the radius gets smaller, just like it would normally. And then the radius gets bigger going top to bottom. So if I look at group 1, I'm like lithium to cation, sodium to cation, potassium to cation, rubidium to cation. Those all get bigger. So it's the same trend as it would be if it was neutral. The biggest difference is that they are smaller as a cation and bigger as an anion.
I just remember on the homework it said if you gain an electron, then it would have bigger radii. So then it was
True.
It was confusing me because it was moving right, which it should be smaller, but then it was bigger.
So I guess I have to look at the question. I don't know if it means gaining an electron as in going from like sodium to magnesium, like technically that one gaining an electron, or is it talking about going from chlorine to chlorine -1? Like which way was it gaining an electron? Like gaining an electron becoming a charge? I'd have to look.
Yeah, it would move right, and then it would say that it was move right along the table.
Okay.
Say that it was a bigger radius, even though it seems like at the bottom left corner it gets bigger and opposite.
All right. How about after class, you just show me the question on mastering? I can help you out. Because I think it depends. I'd have to read the question to see if it's asking what it's specifically asking. Yeah,
Number 21.
21. Why don't you read me 21? Because my numbers don't match
It
yours.
says, what is the maximum number of electrons in atoms that can have the following set of quantum numbers?
Mm-hmm.
N equals 4, L equals 3, M of L is -2, and S positive 1.
Yeah. Okay. Let me find that one. Yep. Okay. All right, so first part of this question is to think in your head. How many quantum numbers do you need to describe an electron? Right, you need 4. 4 numbers to describe an electron. How many quantum numbers did I give you? 4, right? I gave you a specific set of 4 quantum numbers. How many electrons can have that set of 4 quantum numbers? Just 1, right? 1 and only 1 electron can have this set of quantum numbers.
Okay.
Right, for the Pauli exclusion principle, I've given you all 4, so I've given you the general area, the specific area, the orientation, and the spin number. So that describes 1 electron. What if I had given you I've given you 3 numbers. I can now describe 2 because I could have the up or the down version of it. So the less numbers I give you, the more electrons could have that combination of electrons.
Can you explain how to find those electrons in the transition metals?
Oh, like what order they fill?
Yep.
Yes?
I guess.
Okay. I think that's what you're asking. If I answer this question and you're like, that's not it, then we'll do something else.
Okay.
All right, let's look at, I had a good one. Let's see. All right, let's say what's the electron configuration of copper? First, you gotta find copper on the periodic table, right? It's number 29. So how many electrons needs to be in copper? 29, good start. All right, if there are 29 electrons and it is over here right in the center, what should its N value be? How would I figure that out? 4, right? It's in the 4th row, so it has to have at least N equal 4. Okay, 2 options at this point. Oh, first, let me ask this. If I'm saying electron configuration, am I saying write it out in letters and numbers, or am I saying draw it out as platforms? Letters and numbers. Electron configuration means letters and numbers. Orbital diagram, when you hear the word diagram, think picture, and draw me the one with the platforms. So you will get all the credit if you draw it correctly with the right sketch. Less credit if it's still right, but you didn't give me what I asked for. So electron configuration means letters and numbers. Diagram, orbital diagram, means draw me some pictures. All right, so we could draw out all 29 electrons. But that takes a long time. What is a shortcut I could start off with?
Argon.
Argon, right? We could start with argon. And it's a little bracket notation. So I'm saying the first 18 look just like argon. Don't worry about it. So then after argon, we said N would be 4. What comes for what? For S, P, D, okay, S. How many electrons go into the 4s? 2. So now I'm up to 20 electrons. But I'm across the transition metals, which is where it gets funky. So after 4s fills, what fills next? The 3d. All right, how many possible electrons could I put in 3d?
9.
I'm going to put 9, but I could potentially put 10, right? I could put all 10. I'm not going to. How many electrons am I actually going to put in there? 9. And then that'd be it. That'd be the answer. Did they answer it?
Let me think.
Okay. Sarah?
So does it not matter whether we write the whole thing out or use the shortcut method, will it not affect our?
As long as you're right. Yeah. If you put a random element in a bracket, then not so much. Okay.
Okay, so my
You
question
thought
is,
about it.
are the valence in the 3D or the 4S?
Okay. The valence would be the 4s.
Because that's the outermost. And so
Yes.
you can't, like, how do I know to think backwards at that point?
The valence are always in the n level. That's the highest energy.
Okay.
Right? So if n equals 4, that's of higher energy than n equals 3.
So you have to, like, in order to find the valence electrons of the transition metals, you have to do the configurations.
Mhm.
Whereas, like, the other ones you can use like that. Okay.
Yeah. Which is why there's a whole class about transition metals called inorganic chemistry. So we're just, I'm trying to pitch this an exciting class. All right, I'm going to do her question and your question. Oh, it's related to this one? Is this one? Okay. Both really, I'll take hers then yours. Okay.
So if that was transformed into, or made into a cation, would you just do, like, take off the 4s to, if it was like a plus 2?
Yep, so copper always makes +2, and it's because we lose it out the 4s first, which would be its valence electrons.
Okay.
So if I made Cu plus 2, which is its most common form,
Okay.
it would be,
Okay. Yeah.
right, so the valence electrons are these guys, which are the ones you'd lose to make this. Does that answer your question too? No? No. All right, I'm ready for your question then.
So we can only fill how many percent of valence electrons if the E is full?
Ask it again.
Because like,
So if I wanted to make krypton, right, krypton, which would be in the same row but all the way across,
yeah. But there can be, can there be several? There can't be any that have a full P unless they're noble gases.
right,
Because I just get confused with how sometimes you have a P before the other ones. but-
yes.
Okay.
So like a noble gas krypton has D's, like it's considered full when it gets to 4p6.
Because we technically haven't completed the fourth energy level,
You have not.
but we don't have to.
You don't have to.
Full set of valence electrons. It's always just 8.
Right, so that's where, next chapter when we start doing Lewis dot structures, the 8 comes from the fact that the N level has 2 and 6, and so it has 8 in its outermost shell,
Because the other ones have
or on the inside. Technically, this is on the inside of the 4s.
Okay. Well, I just need 8.
Yes. All right, a variety of questions over here.
Should that be 30, 10?
Oh, yep, sorry, 10. Yep, no, sorry, 10. I was just copying, sorry, throwing everybody off. Yeah,
Okay, on the homework, it says that nickel has 10 valence electrons. I wonder if
on the homework it says nickel has what?
10 valence electrons.
10 valence electrons.
What?
Change the role.
So that's where I.
I would not consider all of those valence. I guess that's where I disagree with mastering, so I won't ask a question like that.
Okay.
Yeah,
Nickel has 2 valence electrons. And
yes.
Okay. So
I disagree with how they're
their
counting, so I,
valence- So like, their valence would be like for copper.
they're
it would
saying
be
every,
11.
yeah, they're saying everything past the bracket is valence,
Okay.
right? And I disagree with how they're counting.
Okay.
I would say just the n values that are in the 4 are valence. So the questions won't be that tricky on the test, right? You only have an hour. I got to make the questions pretty straightforward.
Question about the test.
Question about the test, okay.
Will there be stuff in the book that we don't have in the class?
Only if it was covered in the homework,
Okay.
right? So I'm mostly going to be pulling questions from the homework and in class. And so if it's in the book, but it wasn't on the homework, I didn't cover in class,
So,
definitely won't be on there.
okay.
So, and again, the homework has to be harder than the test, right? Homework, you have, in theory, unlimited time to do it, and you get multiple chances. So the homework's always going to be harder than the test. Because in here, I only have 50 minutes to get you to answer as many questions as possible. So there's kind of a balance. So if you can do the homework and you're like, I got this, the test should be pretty straightforward. So that's how I try to write the homework questions. So you're like, these suck. But then the test is like, oh, that wasn't so bad. So, yeah.
Will the test be like multiple choice and then the problem, or?
I think my plan is, as soon as I write it, will be, I'm hoping to get it written today. It's not been a good week for my time management. My plan is to have I usually have 10 multiple choice questions. That's usually and it's usually like the ones that were on the practice test, like which of the following is the largest radius, or which of the following is not an electron configuration that's allowed. Something you can just look at and be like, circle, done. So a third that way. About half, so like a third and a half, and there's going to be a sixth in my fraction making, right? So if there's 6 portions, 1/3 is multiple choice. 1/2 is going to be short problems. So like the one we did over here, how many grams, or how many, using the equation, what's the energy? And it'll be like 1/6, like 1 or 2 questions that's been like on your homework, like why is lithium +1 a smaller radius than lithium? Where you tell me something about, either electron configurations, or is it effective, or something. It's like a short sentence or 2 answer. So short answers. That's my plan. As soon as I get to writing it, any day now. Yeah.
Will we be allowed to bring my periodic table?
I provide you a periodic table. So like the front of your test will look like something like this, where you put your name on top. There's a pledge that says you did not cheat, nor did you witness anyone else cheating. If that is true, then you sign your name. I'll have all the constants you need in this section. A little periodic table, which feel free to tear off. I'll bring a stapler if you want to tear it off and have it side by side with your test. I don't mind that. And then kind of break down the points. And so as you would look through the test, like every question will tell you how many points it's worth. These are the short answer, right? These have like spaces for you to do problems. So I'll bring scrap paper in case you write really, really big and I didn't leave you enough space. Not a problem for Charles. You'll have to work on writing a little bit bigger. And I will have a few spare calculators, but you'll have to bring your own non-graphing calculator. Yes?
Okay, on the homework, isn't that subject consistent of the policy principle, the final and
Alphabet principle. All right, so let's look at I have to look back at my notes. It's not alpha. Use AU. All right, so those are the 3 that are related in a lot of ways. All right, Pauli exclusion principle is the one that kind of rules the other ones. Pauli exclusion says no 2 electrons in a single atom. Can have the same 4 quantum numbers. Right, that's the one that guides all of our other answers.
Does that mean like you can't have N of 4 and L of 4? What does it mean by the same 4 quantum?
Oh, so like that was the question you asked earlier, this one? So this is a set of 4 quantum numbers that no other electron in that atom can have. Because this one's been spoken for. Right, so that's a set of 4 quantum numbers, an M, an L, an N sub L, and M sub S, that refer to a unique electron. And so no other electrons in the atom can have that.
So like another electron in the atom could have the N of 4, L of 3, N of L -2, but the N as a -1/2?
That'd be fine.
Okay.
Yep. That would be totally fine. So really, when we talk about this, that's Pauli's exclusion rule, that every electron has its own spot in the electron, or in the atom. All right, Hund's rule. We fill degenerate orbitals with spin up first. All right, so let's say I have, we'll pick an easy element. Let's do nitrogen. All right, nitrogen has 7 electrons. So where do I start? We'll do an orbital diagram. So we're going to do platforms. So where do I start with my first platform? What's it called? 1s. And then how many electrons am I putting there? 2. Okay, what comes after that? Okay, and how many electrons live in there? 2. I need to draw 2p. How many platforms does 2p get? It gets 3 platforms. So if it gets 2p, how many electrons do I have left to spread across my 2p's? 3. So would I do it? No. What's wrong with that? Yep. So we're going to fill the degenerate orbitals, which are these 3. These 3 are all degenerate. Right? Means I have 3 of the exact same. Spin up first, so that one's wrong. So it should be this way. So Hund's rule says everybody up, then come back and do everybody down. All right, then the Aufbau principle says fill orbitals from lowest energy to highest energy. Which again is what we've been doing, right? We fill the 1s till that's full. Then you go to the 2s till that's full. Then you go to 2p till that's full. So really, the Aufbau principle is what you have been doing. You just haven't been calling it the Aufbau principle.
So, what about configurations that, like, you take the electrons out of the S shell and put them into the P? I swear there was something on the whole mic where, like, you were saying that you took, like, with ions, that you take the electrons out of the S shell and put them into, like, the P shell.
Into the shell.
Yeah, something.
Yeah.
Okay.
I'm not crazy. And then because it's like, it would ask you, like the orbital diagram.
Mm-hmm.
And then it would ask you like where,
With these, like,
2 electrons, so where's the best place to put it, and like we think it's gonna be like 4s or something.
but apparently it's not.
So you have to put it
Somewhere else.
Put it someplace
We
else.
never put it.
If I'm perplexed by that problem, I wouldn't put it on your test. Because I don't, there's no reason to take it out of the S, because you can't have an S until the P is full. Baffling. Okay. I think they're interesting, but there's not a good way to ask a question about them. About the specific experiments and the specific names and the dates and whatever, like they're fascinating. But you don't have to know the specifics of any given experiment that we did. So, unless you're totally interested in it, in which case, yes, definitely know them, but it will not be on the test. Other questions? We got like another 10 minutes. I could create some questions. Yes? All right, let me try that then. What I'll do is I'll come up with 2 or 3 questions. You guys can work in your vicinity. Let's see. Oh, you got one?
No, it just wasn't walking. We had friends and stuff. And then they go back outside, have a little place. Don't ask about it. I probably will.
All right, so what element? Yeah, you're just faster than me. Takes me longer to write them. How are we doing on this one? All right, so which element do we know has the greatest electronegativity? Fluorine. Fluorine has the greatest, and which one has the least? Well, which, besides the noble gases, what element has the least?
Wait, which element?
Which one has the most? Fluorine, besides the noble gases, which are all 0. What element has the smallest? francium, right? So looking through our choices, would lithium have high electronegativity? No, that's a terrible choice. All right, let's find AS, number 33. Maybe, right? That's not terrible. What about potassium? No. All right, so then we're left with between arsenic and nitrogen. Which one is closer to fluorine? All right, working your way through it. A lot of the multiple choice questions are going to be like this, where if you can eliminate two, you can make a really good guess between what's left. All right, if I'm looking at electron configurations, how do I find elements with similar properties? Do I look across or do I look up and down? Right, I look up and down. So I want two elements to have the same electron configuration. If they're up and down, do they have the same core, the same valence, both, neither? Same valence. Why don't they have the same core? Because I'm adding electrons as I go across, right? And so if I'm in the sodium row compared to the potassium row, I have a whole nother energy level. So the cores can't be the same. Well, they're going to be similar, but not identical. So I want number of valence electrons. So looking at that, would A be a good choice? No. Why is A a bad choice? All right, because this one has 6 valence, and looking at just the 4s, right? Or you can even figure out which elements these are if you wanted to. Right, what element is 1s2, 2s2? Right, that one's oxygen. And then arsenic plus 15 more. 1, 2, 3. Let's see, where am I at? 3d10, 4. That's arsenic. Are those in the same up and down? No, they're off by 1. All right, this is arsenic again. What about 1s2, 2s2, 2p5? All right, that's F. Is F and arsenic in the same up and down? No, that's not good either. All right, so now I have oxygen, and by process of elimination, this should be the right one, assuming I didn't mess something up. All right, this would be selenium. Should those have similar properties? Yes, good, I didn't mess up that problem. All right, how about which of the following are allowed sets of quantum numbers? Choice number 1 would be n equals 1, l equals 0, m spell equals -1. Is that allowed? No, what's wrong? Yeah, this guy's not right. You can't have an m sub l greater than L. Okay, so that's a no. What about would that be allowed? Yeah, okay, that's a good choice. Good. What about oh, what happened there? No, that's not, nope, that's wrong right there. What about oh, what went wrong? Oh, man, look at my MS. That's not good, not good. All right.
You only do multiple choice, right? Not multiple choice.
I don't do multiple choice, and I don't do correctable multiple choice. Unless you want me to. Huh? Oh, no, okay. Correctable true false? No? Okay. Correctable means like, so for this one it was wrong, you would tell me it's wrong and then fix it to make it right. No, okay. I could do that, but it's a lot of work. A lot of work, so. Anything else? No? Feeling good? Alrighty. Go team chemistry. Go steady.